Welcome everyone to today's seminar. Today we have Guilherme Limberg, who is a last year PhD candidate at USP. And starting in October 2024, he will be an independent postdoctoral fellow at the Kavli Institute for Cosmological Physics at the University of Chicago. Guilherme, are you ready? When you're ready.
Yeah, sure. Okay, so can you hear me well?
Yes.
Okay, so hi everyone. I'm so happy to be presenting this work to you guys. Just like Ana just said, I'm Guilherme. I am a finishing PhD candidate at IAG, and I am also an incoming fellow at the University of Chicago, an incoming postdoctoral fellow. And funny enough, although this talk I'm going to be discussing mostly things about stars and galaxies, have been hired by the Cosmological Physics Department at the University of Chicago, so go figure. And yeah, throughout this talk, I'm going to talk about this topic of the R process enrichment in dwarf galaxies. So just for us to have a broad idea of how this is going to work, I really like this figure. This is a figure from a recent review kind of paper. It's actually from nuclear physics handbook kind of thing. And this is kind of a scheme showing how we work in this field that we call galactic archaeology or stellar archaeology. So what happens is that, like at early times, right after the Big Bang, we have the early galaxy formation and the formation of the first stars. And after 13 billion years of evolution, we have like these dwarf galaxies that have been formed. They fall into the halo of our galaxy. They are accreted, or they are just become bound and become the classical dwarf galaxies that we know and love, like the LMC or the SMC. And over this 13 billion years of evolution, we have chemical evolution and star formation happening in the systems. And nowadays, we can actually observe and study these dwarf galaxies by looking at the chemical compositions of individual stars in these galaxies. So this is just to show a little bit of how this is going to work, or how this field of galactic archaeology works, that we can actually rewind the star formation history and the chemical evolution of dwarf galaxies or galaxies in general by looking at the chemical compositions of individual stars in them. And so just to begin with, I promised that this would be a talk about the R process. But what is the R process? So in order for me to explain that, I'm going to start with this periodic table. So this is just a periodic table that we learned like in high school or something. But this is color-coded by the main source, the main nucleosynthesis source for every specific element, the most important nucleosynthesis astrophysical site for every single of these elements. So in the upper portion of this periodic table, we have the light elements. So these light elements are mostly produced as we can see in pink, by the explosions of massive stars. So by classical core collapse supernova. We also have the elements in brown. These are all of the elements that are around the atomic number of iron. So you can see iron, you can see also manganese and cobalt and nickel and other elements that are painted in brown right here. These are coming from, following the caption of this figure, these are coming from exploding white dwarfs. These are coming from type 1a supernova. And then we have the bottom portion of the periodic table. And this is the portion of the periodic table that we care about for the purpose of this talk. These are the heavier elements in the periodic table. So a bunch of these heavy elements, they are produced, as we can see, in dark blue. These are producing by dying low mass stars. And by dying low mass stars in this caption, what we mean is basically by AGB stars. So AGB stars throughout stellar evolution, they can actually produce these heavier elements. And then at the late stages of evolution, they actually can eject this enriched material through just stellar winds, and they can pollute the interstellar medium of a galaxy. But then, for the purpose of this talk, what we care more about is about the light blue elements in this periodic table. So these light blue elements are produced in environments that require very neutron, a very rich neutron environments, where the R process and this R process can operate. So what does R process stand for? This R process is what we call the rapid neutron capture process. And what happens in this scenario is, imagine, for instance, right here, I'm showing an example of an environment where you have a seed nuclei. A seed nucleus, in this case, this is a nucleus of iron, just for the purpose of this example. And this seed nucleus is in this environment where you have a bunch of free neutrons. And in this environment where you have a bunch of free neutrons, this is a very dense, neutron-dense environment. And what can happen is that this seed nucleus, like in this case, iron, can be just literally, this is the word that we use for it, it can be bombarded by this bunch of free neutrons. And then you create this very rich, very neutron-rich nucleus that can then just that is very unstable because like free neutrons are unstable, and you can imagine that the time scales for this process, it has to be very, very fast because free neutrons are unstable. And then what happens is that after you have this very neutron-rich nucleus, you can just beta decay back into stability. So then becoming a nucleus for an element that is one of those heavy elements from the periodic table, for example, gold. So gold is mainly produced in this environment. So in nature, where we know we can actually find this very neutron-rich material, this material that is very rich in these free neutrons, is by just ripping material out of neutron stars. So, and we can actually do this either during the birth of a neutron star or during the death of a neutron star. And one example is this one. This is showing one example where neutron stars can die in a way. And these are in neutron star mergers. So if you have like two neutron stars that are in spiraling, they can eventually just merge through like gravitational radiation. They just get closer and closer until they actually merge. And then the ejecta of this neutron star merger is going to be very rich in free neutrons. And in the ejecta of this neutron star merger, this R process, this rapid neutron capture process can actually operate. Okay, so having said that, I just mentioned that we can actually create this very neutron-rich environment by ripping material out of neutron stars, both in the death or in the birth of a neutron star. I just mentioned the case for the death of a neutron star, which could be, for instance, in neutron star mergers. But then, if you think about it, the birth of neutron stars happen during core collapse supernova. We have actually never observed a core collapse supernova producing these very heavy elements or a bunch of these R process elements. However, this is actually very theoretically promising. We do have a bunch of models, like for instance, this one from this paper from 2014, so 10 years ago now, that shows that if we have this weird kind of supernova that has a lot of rotation and sometimes have very strong magnetic fields, what they call magnetorotational supernova, you can actually have an environment that is rich enough in neutrons, in free neutrons, that you can actually create our process elements. So the situation is that we actually have two channels that through which our process could be created. They are very theoretically promising. And however, we actually have observed one neutron star merger. Back in 2017, we actually observed the event GW170817. This is a gravitational wave event of a neutron star merger. And then after that neutron star merger event, we actually found the actual transient for that kilonova, which is the transient created by the neutron star merger. So the situation right now is that although theoretically both of these environments could create these very heavy elements, what happens is that we actually know that, we definitely do know that neutron star mergers, they do happen and they do make our process, while core collapse supernova or these weird kinds of core collapse supernova, they are promising theoretically, but we are still lacking observational evidence. And indeed, just like now moving on that, this is the event that I just mentioned, the neutron star merger event of the neutron star merger GW170817. So, and right here on the left, we can see the transient of that kilonova that I just mentioned, which is the transient associated with the merging of two neutron stars in this galaxy. So one thing that is very important from this figure, I think for the purpose of this talk, is that the environment where this neutron star merger actually happened. So if we take a look at the host galaxy of this neutron star merger, this is an early type galaxy. This is a massive, very quenched galaxy that has basically already formed all of the stars that is ever going to form, right? So the situation is that maybe because it takes a long time for these neutron star mergers to coalesce through gravitational radiation, what happens is that maybe these neutron star mergers, although they do explode and they do make our process, they are just exploding in the middle of nowhere. And this R process rich material, these R process elements, these very heavy elements, are just never making their way back into stars and planets. So maybe the main source of our process in our own planet, like planet Earth, wouldn't be neutron star mergers because of these delay times that are so large, because we need to wait for these neutron star mergers to coalesce through gravitational radiation, and this takes a lot of time. And this is the case for this galaxy. Like the neutron star merger that happened right here created heavy elements, a lot of heavy elements, but they are just never going to make their way back into stars. So this is the situation right now, is that although we do know that neutron star mergers, they do happen, they might be just happening in the middle of nowhere and not actually contributing to the chemical enrichment of galaxies because of these delay times. And then the second, now moving on to another observation of our process elements that is very important. So gravitational wave detection of the neutron star merger event was the most important observation that has basically ever been made in the topic of understanding the origin of these very heavy elements. However, 1 year before that, in 2016, there was actually observations of this one dwarf galaxy right here. So this is a field that basically it looks like there's no galaxy at all, because this is a very low mass galaxy. This is a galaxy that we call a Neutron dwarf galaxy. This has only 10 to the 4 solar masses of stellar mass. This is a very low mass galaxy, and this galaxy is called Reticulum II. So this is in this very low mass galaxy, just for us to kind of have a notion of how do you actually find these galaxies, because they are so faint. What you can do is you can just like take deep photometry out of your entire sky, and this is done with the dark energy survey. You can just take your photometry, and then by looking in, not only looking spatially for overdensities on the sky that would be characteristic of dwarf galaxies, you can actually just look, combine that spatial information with the information of your color magnitude diagram. So you can just take a color magnitude diagram of a very old metal pore stellar population, and then by just filtering in your photometry, spatially, you can actually find these overdensities of stars that, although they are not super dense, spatially, they are coming from a stellar population that is very consistent with this very old and metal pore stellar populations from this isochrone kind of search. And this is what happens, and this is how you can find these very low mass dwarf galaxies. And by taking observations of these high-resolution spectroscopic observations of these low-mass dwarf galaxies, what you can do is to do what I mentioned in the beginning, which is to measure the chemical compositions of these stars. And what happened for this one galaxy is that this one galaxy, Reticulum II, is immensely rich in our process elements. So these are the chemical abundances of stars in this Reticulum II galaxy. In the vertical axis, we have europium, which is our best tracer for the R process elements, simply because it has the best lines for us to measure in the optical wavelength. And then in the horizontal axis, we have this FeOH, which is kind of just a proxy for the metallicity. But what really matters right here is the vertical axis. And you can see that stars from this Reticulum II galaxy, which are the orange points right here, they are, and this is a log scale, right? So this is these stars from Reticulum II, from this one galaxy, they are basically at least 100 times more enriched in this R process element europium in comparison to other ultra-faint dwarf galaxies, which are marked right here with these open symbols with different colors. So what happens? So one of the things that we can get out of this is that in one hand, one of the things that what people believe that has happened in this galaxy is that because this galaxy is so low mass, what must be happening, or what people think happens, is that a single R process event, like a single neutron star merger or a single one of those weird kinds of core collapse supernova exploded in this system, and then just one single R process event enriched the whole galaxy. So, and by taking a look at other dwarf galaxies that are similar to this, what we can infer from this observation is that these R process events, they have to be really rare, because only one out of like several of these ultra-faint dwarf galaxies has this R process enrichment. And on the other hand, this process has to be prolific, because a single event must have created a bunch of these elements, a whole lot of R process material, a whole lot of these very heavy elements. So the scenario that we can envision is the following. So if you think about a bunch of ultra-faint dwarf galaxies, so in this case, I'm taking 10 ultra-faint dwarf galaxies, which are these clouds with a bunch of stars. Most of them have no R process at all, because these events are so rare. This, for instance, neutron star merger events are so rare, they don't actually happen enough for you to have a bunch of these small galaxies enriched in R process elements. However, Reticulum II ended up being the lucky one or the unlucky one that has had one of these R process events happening in it. I don't know if it's we don't know if it's a fast merging neutron star, if it's a neutron star merger that happened in this galaxy, or if it's one of those weird kinds of core collapse supernova. But we know that from these observations that these R-process events must be very rare, because you need a total of 10 of these ultra-faint dwarf galaxies. This is going to be like 10 to the 5 solar masses in stellar mass. And then for you to have only one of these R-process events. So this is what we can infer from these observations. But also, and what I think is very interesting is that not only we can infer that these R-process events are very rare, but we can also infer what is the time scale for the occurrence of this R-process event, because we can just take a look at the amount of stars in Reticulum II, the fraction of stars in Reticulum II that are enriched in these R-process elements, and then compare that to the star formation history of this galaxy. And how this works is the following. We can just take the star formation history of Reticulum II, which is the gray band right here. You can see that most of the stellar population of this galaxy was formed really, really fast. Basically, what happens is that these ultra-faint dwarf galaxies, they have these very short star formation histories, or their duration of star formation is very short, because these ultra-faint dwarf galaxies, they are just basically fried by reionization. So you are forming your stars, but these galaxies, when reionization happens, basically you just cannot form stars after that. And what happens is that out of the stars that we have observed in Reticulum II, about 70% of those stars have been enriched in R-process elements, which means that basically the R-process event that happened in this galaxy must have happened somewhere around here, which means that this should have been like very, very fast. So this is kind of like the situation is that in this, at least in this Reticulum II galaxy, the R-process event that happened in it must have been really, really fast because of the star formation history. So we don't know if it's some weird kind of like supernova, core collapse supernova, which are going to be one of these like fast kind of sources for the R process, or if it's some weird kind of like fast merging neutron star. So this is the situation, because we would expect that neutron star mergers would take so long that with such a short star formation, so long to happen, that such a short star formation history wouldn't allow for this galaxy to be enriched by one of these neutron star mergers, but we don't know for sure. And then, so what is happening right here is that this ultra-faint, and this is not, basically this happens to all of the ultra-faint dwarf galaxies. All of these ultra-faint dwarf galaxies, they are all just quenched by reionization, and then they basically stop forming their stars really early. But then, if we take a look at other dwarf galaxies, like the classical Milky Way dwarf spheroidal galaxies, or other classical dwarf galaxies like the LMC or the SMC, they have much more extended star formation histories. And in a way, this kind of makes sense. While these ultra-faint dwarf galaxies, they are just quenched by reionization. If you're very massive and you have a lot of gas, why would you ever stop forming your stars, right? So, and this is what happens for the Milky Way. On the left, we have the ultra-faint dwarf galaxies, and on the right, we have the classical Milky Way satellites, these dwarf spheroidal galaxies like Fornax or Sculptor and other satellites. And then, just so we are not just following kind of our intuition, and if you want to like see if this is actually something that is weird about the Milky Way or not, we can actually take a look. Okay, so I guess the figure did not show up in my slides, so I guess we are just going to move forward. So basically taking from this figure, what we can infer is that in ultra-faint dwarf galaxies, we do not expect to see the signatures of a neutron star merger happening. Maybe we could see the signature of neutron star mergers happening in the classical dwarf galaxies that have much more extended star formation histories. And basically what would happen is that because these neutron star mergers are delayed, they take a long time to start happening after the beginning of star formation. What would happen is that these classical Milky Way dwarf galaxies that have extended star formation histories, they would have had enough time for you to just start exploding your neutron star mergers and for you to be enriched in R process elements really by neutron star mergers. So this is basically one avenue from which we could actually try to test if neutron star mergers are actually contributing to the chemical enrichment of galaxies, or it's the first scenario that I presented that they are just exploding in quenched galaxies and never making their way back into stars. So then, if we take a look, how do we look at this? So just again, going for, this is basically the same chemical composition, chemical abundance panel that I showed for Reticulum II. But now I'm just explaining a little bit more. So on the horizontal axis, we have, again, the metallicity, which is going to be our proxy for time. So as a function of time, these dwarf galaxies, they get more and more enriched in metals. And so as a function of time, metallicity is going to increase. So basically, we can use some, for example, like some element that is going to be tracing the metallicity, tracing the overall chemical enrichment of this dwarf galaxy, for instance, an element that is produced by the core collapse supernova, because core collapse supernova are still dominating the chemical enrichment. For instance, magnesium. Magnesium is one element that is very easy for us to measure, have very strong lines, so we can just go out there and measure. And then in the vertical axis, what we can have is one of those R process element kind of elements. So again, European is the best R process element that we have for us to observationally, for us to measure. And then we can draw, then we can use the ratio between this R process element, again, just like in the case for Reticulum II. And the ratio, we can actually put in the vertical axis, the ratio between the R process element abundances and basically the amount of R process events that happen in the galaxy. And we can put that in a ratio with the amount of chemical enrichment that is coming from just regular core collapse supernova. So we can use magnesium again, basically here. So we are basically trying to take a look at what is the evolution of these R process elements in comparison, or the abundance of these R process elements in comparison to the elements that are created by just regular core collapse supernova. So what we would expect is that if you are having like enrichment in these R process elements exclusively from neutron star mergers, what would happen is that you would just come from like basically nothing of our process, and this is a log scale in comparison to the sun. So 0 here is the abundance of the sun for any given element. And basically you're coming from minus infinity in this scale, so coming from no R process elements at all, so no European at all. And then you just create a bunch of R process elements in a single shot by neutron star mergers, and then you have this increasing trend over time, because as a function of time, you have more and more neutron star mergers, because again, this process is delayed. So as a function of time, you just have more and more enrichment in these R process elements because you have more and more neutron star mergers. But then if you think of another scenario of these galaxies not being enriched by just neutron star mergers, but being enriched by neutron star mergers plus core collapse supernova, those magneto-rotational supernova that I mentioned in the beginning of the talk, you would expect something like the rising trend, which is associated with the beginning of the neutron star merger enrichment, but at a low metallicity, in the low metallicity range, like at early times in these dwarf galaxies, you would see some kind of plateau trend, which would be the characteristic enrichment that is coming from just core collapse supernova alone. And then so this is the most basic prediction that we can make for this kinds of enrichment by neutron star mergers with neutron star, this enrichment of dwarf galaxies, with neutron star mergers. And you either have just forever increasing trend in the R process because you have only neutron star mergers, or you have neutron star mergers plus a plateau. But then, if we take a look at the data for dwarf galaxies, for true dwarf galaxies, this is what we see. So this is what we actually measure from individual stars in these dwarf galaxies, which is what I mentioned, which is that this European over magnesium ratio, magnesium a tracer of the overall metallicity, of the overall enrichment by just regular core collapse supernova, and European is our tracer element for the R process, and magnesium over hydrogen here representing just the metallicity of your galaxy, or just time for that matter. If we take a look at the data for like true classical dwarf spheroidal galaxies, this is what we see, or people propose that we see, which is this exact prediction of a plateau and then an enrichment in our process in this fornax dwarf spheroidal galaxy. And then we just have a single plateau in this sculptor dwarf spheroidal galaxy. So this is what the trends that we see in the data, or that is coming from this paper right here. So what happens for this sculptor dwarf galaxy not to be enriched in our process elements as much as fornax? What people propose is exactly that situation with the star formation histories. So the star formation history of sculptor looks something like this. It's a very short duration star formation history, while fornax is forming stars over a much more extended period. So the star formation history of fornax is much more extended. So basically what people propose, looking at these trends in our process elements, is that the sculptor just did not have enough time for it to have neutron star mergers happening. So neutron star mergers start happening somewhere around here. And then fornax can be enriched in these R-process elements because it has an extended star formation history. While with Sculptor, when you start exploding neutron star mergers, you are not forming any stars anymore. So your R-process elements never make their way back into the stellar population of Sculptor. Okay, so this is very good. Having said that, if we take a look at the actual data, not just these trends that are proposed from this paper right here, what we see is actually this. So this is just a lot of scatter, in my opinion. Maybe the situation that I just mentioned, that fornax, this dwarf spheroidal fornax is actually more enriched in our process elements in comparison to this core collapse supernova kind of tracer magnesium, exactly because it has a more extended star formation history, just like it's proposed. But you say that, but you claim that this right here is a plateau. I think it is a little bit difficult to say, just because, and also you are just claiming this scenario based on two different galaxies. And I just mentioned that these predictions of this rising trend with metallicity for the R-process element is the most basic prediction that we can make. So we would really like to do is to take a look at a single galaxy that shows this increasing trend. And instead of just looking at two different galaxies where, in order for you to make these claims, you're actually folding in a bunch of like assumptions regarding your chemical evolution. And also, we cannot really distinguish from this data if it is just a single rise in the R process, like the situation with only neutron star mergers, or if there's really a plateau right here. This is just half a dex. So this is not a very large metallicity range, but in which we can actually make tests of chemical evolution. So what we really would like to do is to go to the more metal pore regime in these galaxies in order for you to really trace this whole evolution of these R process elements as a function of a much larger range of metallicity. But this is very difficult to do. This is very difficult to do specifically in these dwarf galaxies because they are very, very far away. And for us to measure the abundances of specifically these R process elements, specifically European, what you need is high resolution spectroscopy. And we cannot just do high resolution spectroscopy of like thousands and thousands of stars in these dwarf galaxies. This is just observationally, this is impossible. And even if it did, it's actually very difficult because you actually need to probe this metal pore regime. And metal pore stars are very rare. So in the Milky Way itself, if you go from the metallicity of this minus 1.5 right here in this scale, if you go to minus 2.5, you would be talking about a decrease in the amount of stars that we have, like even in a halo of our galaxy, of a factor of 10. So if you go to more and more metal pore, your stars become more and more difficult to find. So this is the situation. It is very difficult for us to test this scenario with these surviving classical dwarf galaxies because they are so far away and because this metal pore regime is so difficult for you to actually probe. So what is the situation right now? So the situation is that we would like to have at least one galaxy where we actually see the whole evolution, this rising trend, this increasing trend of our process as a function of metallicity in a single galaxy, instead of just folding in a bunch of assumptions and a bunch of like things regarding the different star formation histories and the different chemical evolutions of different galaxies. But also, we would like to test, since I just mentioned that the star formation history is very important for you to really understand what is happening, what is the timescales for the occurrence of these neutron star mergers, what we would really like to do is to test what is the minimum star formation duration that you need, what is the minimum amount of time that you need for your system to really be dominated by chemical enrichment in neutron star mergers. And then also because this enrichment in neutron star mergers also depend on the mass of your galaxy, because if you have a low mass galaxy like Reticulum II that I mentioned in the beginning, you are basically just dominated by the rarity of your event. You're just dominated by stochastic chemical enrichment. We would really like to know what is the minimum mass for a galaxy to have chemical enrichment dominated by neutron star mergers. So to kind of like simplify what we really want to would like to do, we can take a look at this figure. So this figure is in the vertical axis. I have the star formation duration of a galaxy. Formally, this is like what is the time for you to form 90% of the stellar mass of a given galaxy. And in the horizontal axis, I have the luminosity of galaxies. So this is a proxy for the stellar mass. And there is even a correspondence to stellar mass right here on the top if you assume some mass to light ratio. And then if we plot, basically, if we go back to this, to what we have discussing until now, what we are talking about is that if you have an extended star formation history, if you have a long star formation duration, what should happen is that your system should be dominated by this delayed R process enrichment, by neutron star mergers. And if we have a very short duration of your star formation, have a very short star formation history, you should be dominated by fast sources of our process, probably core collapse supernova, maybe fast merging neutron stars, but who knows? And then in the horizontal axis, which might be not as obvious, is again that your stellar mass is also important for this. Because if you go to the low mass systems, to like the Reticulum II kind of systems, those ultra faint dwarf galaxies, your chemical enrichment is just dominated by stochastic enrichment because your sources of our process are so rare. So, but then if you go to high mass systems like Sculptor or Fornax, you should be not be dominated by the rarity of your events anymore because you're just averaging over enough of your IMF. So you just have enough star formation and enough stellar mass that you just have a bunch of like this neutron star mergers or this R process events for that matter, that you can just average out your chemical enrichment and really have like some kind of smooth chemical evolution for these systems. And so if we plot the Milky Way satellites in this figure, what we have is something like this. And just like I said, these things are correlated, right? If you have a low mass system like ultra faint dwarf galaxies, they are just quenched by reionization and never form stars ever again. And if we go to high mass systems, again, you have long star formation duration, you have extended star formation histories, because if you have a lot of mass, if you have a lot of gas, why would you ever stop forming stars? And so, but what we really like to do is, just like I said, not only to see a single galaxy that has been enriched in neutron star mergers by seeing the rising trend in a single galaxy, which is very difficult with this surviving satellite galaxies of the Milky Way because they are just so far away that we cannot have enough measurements of high resolution spectroscopy in stars covering a large enough metallicity range that we can just not do this with these galaxies, or it's very difficult to do it with these galaxies. But also we would like to test what is the minimum amount of star formation duration that we need for your system to be really dominated by neutron star mergers, and what is the minimum mass. However, what happens is that you can actually end up with a galaxy in this region right here for you to probe more of this parameter space. If you have a satellite galaxy that just falls into the halo of our galaxy, gets accreted and gets tidally disrupted, and then what happens is that the star formation history of this accreted galaxy is just interrupted by tidal disruption. So just to have a sense of this, I have here this simulation. So I'll be speaking while the simulation runs. So this simulation is showing the formation of a Milky Way mass galaxy in the center right here, and in a cosmological context. So this is a chemodynamical kind of simulation. Basically, what I want us to see in this simulation is that this central Milky Way mass galaxy right here is growing by accreting a bunch of small satellite galaxies that are just floating around it. So by this accretion of these like low mass dwarf galaxies, this galaxy is not only like growing itself, but also it's forming its stellar halo. So these accreted stars from these accreted dwarf galaxies are going to end up in the halo of this simulated Milky Way mass galaxy. And so indeed, using Gaia, we have actually discovered by using phase space information from Gaia, so especially proper motions from Gaia, but also radial velocities and also the parallaxes that are provided from Gaia, we have actually discovered a bunch of these disrupted dwarf galaxies inside the halo of our Milky Way itself. So we can actually just use the kinematics of stars that are coming from Gaia to group together stars in the halo of our galaxy that have similar kinematics, and these are just coming from the same dwarf galaxies. And so how this works is that if we have like our galaxy and it has its inner and outer halos, what should happen is that the halo of our galaxy following that simulation should look something like the figure on the right. So the figure on the right is just a halo of a Milky Way mass galaxy from these Aquarius simulations. And this figure to the right is actually color-coded by the progenitor system. Each particle is color-coded by the progenitor system, the progenitor dwarf galaxy that they are coming from in the simulation. And what we see is that in this simulation, we have different systems in different stages of what we call phase-space mixing. We have, for instance, the yellow particles right here. They are just very well mixed into the halo of the galaxy. They are already forming like this kind of isotropic distribution around the center of the galaxy in the simulation. We also have those galaxies that are still in the middle of tidal disruption process. For instance, these magenta points or pink points right here crossing across like the simulated galaxy. These are still kind of like spatially cohesive in these elongated structures, and these elongated structures we call stellar strings. So we can also find galaxies that are in the middle of this accretion process. They are still kinematically and spatially cohesive, like the magenta points right here in the simulation that we call stellar strings. And we can also see the normal dwarf galaxies, the just intact dwarf galaxies. For instance, like the SMC or the LMC, which could be like in the simulation, these particles, these green particles right here in the top, which could be just some regular dwarf galaxy, some classical dwarf galaxy like the SMC and the LMC. And then what happens in order for us to do this, in order for us to really kind of color code the halo of our own galaxy from observations like we do in simulation, what we can do is just use kinematics, like I mentioned. So this simulation right here on the left, it's just throwing kind of simulated galaxies into a potential a galactic gravitational potential that is similar to the potential of our own Milky Way. What happens throughout the simulation is that these galaxies that are being thrown into this potential, they just get more and more mixed, which is happening to this dark blue points right here. However, in the right panel, in this energy versus angular momentum space, what happens is that these galaxies never move. So these quantities, these energy and angular momentum quantities, they are just conserved. So independent, I'll let the simulation just run again. So independent on the stage of phase mixing that a given accreted galaxy is, you can still recover which stars belong to each other to the same progenitor dwarf galaxy, the same progenitor accreted system, by just clustering them in this energy and angular momentum kind of space, because these quantities are just conserved. And this is how we find a bunch of these, this is how people found a bunch of these disrupted dwarf galaxies. So what is interesting from this is that here I'm marking with a check mark the ones that are definitely real, with a question mark the ones that we don't know if they are real, and with an axis the ones that are irrelevant because these are just in situ kind of structures. So by combining Gaia with spectroscopic surveys, in this case for this paper specifically, it's data from the H3 survey in the northern hemisphere. What you can do is just calculate those quantities, those energy and angular momentum quantities, and just cluster them stars together to find like this accreted kind of populations. And so what we ended up doing is just doing that R process enrichment kind of work, just looking at the chemical compositions of stars from some of these accreted systems. These have not only the advantage that they are probing that different kind of parameter space, we can actually extend the parameter space for which we are exploring the enrichment in R process elements by neutron star mergers, but also stars from this system, they are just much closer than surviving dwarf galaxies. These are just stars that are in the halo of our own Milky Way. So what we can do is we can just go out there and do high resolution spectroscopy to measure the R process elements in a bunch of these things. And by doing so, this is what we find. So this is the work that we did for one of these dwarf galaxies that have been accreted. As you can see on the sky, they look like this here on the bottom right part. So they are just a stellar string. This is just a stellar string. These stars are still kinematically and spatially cohesive in the halo of our galaxy. So they are kind of in the intermediary stage of tidal disruption that I mentioned during the simulations. And the chemical compositions that we see are like this. So this is the same panel that I showed for Fornax and for Sculptor. This is europium over magnesium as a function of magnesium as tracer for the metallicity. And as we can see, the ratio between europium, the R process element, and magnesium, the element that is just tracing the overall metallicity of the galaxy, is just increases as a function of metallicity. And not only it increases as a function of metallicity, but this is also covering a much larger metallicity range than what was being covered for Sculptor. So this is the first time that we actually see this rising trend of the arc process in a single galaxy. And we can see that in this system because this is a stellar string. So the stars are just much closer that we can just go out there and do these measurements. And if we plot on top of this, those kind of like toy models that I was like showing in the beginning, this is what we have. So we still are not probing metal pore enough for us to distinguish between these two scenarios where we have neutron star mergers alone or core collapse supernova plus neutron star mergers. But what these observations tell us is that neutron star mergers, not only they do happen, but they happen in a time scale that is fast enough that you can have dwarf galaxies. You can have entire galaxies that have our process element enrichment that are dominated by neutron star mergers. Neutron star mergers are the main source of our process, at least in this one galaxy, because we see this rising trend. And then we actually went out there and did this for another galaxy. We did this for this blue thing right here. This is a dwarf galaxy that is actually much more massive than that previous stellar string that I showed. This is what people call the Gaia sausage Enceladus. What you can see is that people give funny names to these things. And what happens here is that we are covering basically the same metallicity range. We are covering more metal rich, but metal rich doesn't matter, right? So we are covering more metal pore, that's basically the same metallicity range. But what happens is that this Gaia sausage Enceladus galaxy, these blue points right here, they are coming from a much more massive galaxy that gets chemically enriched much faster. So at the same metallicity, these stars from these blue stars from this Gaia sausage Enceladus thing, they are older than the stars from the other stellar string, the yellow points right here. And so what happens is that what I thought was going to happen is that, and this is the part that is very frustrating to me, is that what I thought is that by going more metal pore, we would actually be able to tell the difference. We just would be able to just straight up tell the difference between core collapse supernova and neutron star mergers at early times, whether you have only neutron star mergers or if you have some contribution of core collapse supernova. However, what happens is that when you go to the more metal pore regime, when you go to the early chemical enrichment in these galaxies, because they are still forming their early generations of stars, what happens that you're going back to the low mass regime because these galaxies still haven't formed most of their stellar mass. So you're going to the low mass regime when you go to the metal pore regime. So you go back to that stochastic enrichment kind of scenario that we saw for Reticulum II. The scenario where you are dominated by the rarity of your events, you have this stochastic chemical enrichment. So basically what this means is that you just have more scatter when you go to more and more metal pore. And this is the natural expectation, actually. I just hadn't thought about that before doing this work. However, even so, by just going even more metal pore and just by measuring how the actual scatter in the abundances behave as a function of metallicity is actually very useful for us to tell if the chemical enrichment is coming from just core collapse supernova or just neutron star mergers. Because if you have higher scatter, you would believe that you have only neutron star mergers, because if you have an additional source of our process on top of that, you would just lower the scatter because you would have more our process events happening. So even though we could not just straight up tell what is the difference between core collapse supernova plus neutron star mergers from neutron star mergers alone, this is giving us a path forward. Just going more metal pore and just from the abundance scatter, we could actually tell us the difference. So just what we should do moving forward. So I have going back to that figure of star formation duration as a versus the stellar mass. I think we should just go out to more systems. Just like I said, one of the questions is not only if core collapse supernova are contributing, because now we have already answered that neutron star mergers alone, neutron star mergers, they do happen and they do enrich galaxies with our process elements. What we need to do now is to go to lower masses to probe what is the minimum mass for your galaxy to be dominated by neutron star mergers, and going lower or like shorter star formation duration. So going down going to the bottom of like this parameter space right here. For 2024b, I actually have like some proposals to get high resolution spectroscopy for stars in these two things right here. These are two dwarf galaxy stellar strings that we have. These are very low mass. You can see that they have high star formation duration here, not because these are the actual star formation durations of these galaxies. These are just the accretion redshifts of these stellar strings, but this is the best that we can do actually for these things. And I'm very excited actually for these two surveys. The S5 survey is a survey, S5 stands for Southern Stellar String Spectroscopic Survey. This is a survey that is taking spectroscopy for a bunch of things that are just tidally disrupting in the southern hemisphere, as you can see right here, the footprint. So this is taking observations of a bunch of stellar strings. So I'm actually getting the targets from this spectroscopic survey because now we have radar velocities to confirm the membership of these stars, individual stars, to these stellar strings. And then I'm actually using the targets from the S5 survey for this program on these other two stellar strings. But another survey that I'm really excited for is this MAGIC survey. This MAGIC survey is a survey with a narrow band filter centered on the calcium H and K line. So this is a metallicity sensitive photometry with the dark energy camera. And it's going to target a bunch of dwarf galaxies in the southern hemisphere, including those two that I mentioned that are Sculptor and Fornax. So I'm mostly excited for Fornax because we can actually now, using this metallicity sensitive photometry, just get photometry for everything in the field of view. And then you can just find the more metal poor stars in these dwarf galaxies and then just go out there and do targeted spectroscopy follow-up for the most metal poor stuff in these dwarf galaxies. And then you can actually do the R process thing in the surviving dwarf galaxies. Even though they are so far away, you can just find the brightest metal poor stars in these systems with this survey. I guess I am running out of time, so I'll just leave you with these conclusions, and I'll answer any questions that you might have. Thank you.
Thank you, Guilherme. Questions? I just turn on the lights. Everyone's like
Cool.
blinded. Questions from the audience? Questions from Zoom? Rogério? Can you go? Do you hear from?
Can you hear me?
I can hear well, yeah.
Okay, so in Portuguese or English?
Whatever you prefer, whatever you guys think is better.
Okay, so if I correctly got, you are trying to measure metallicity and R process sensitive features on stars, okay? And you are trying to connect this with the star formation history of the galaxies. So my question is, how long does it take to incorporate on the atmospheres of the stars those R process elements?
Okay, so yeah, basically when you do the spectroscopic analysis, these stellar atmosphere models that we have just from like public libraries of stellar atmospheres, like Max models of atmospheres, they just basically get your R process scale to the solar abundance. And then what you do, you take this stellar atmosphere models, this is of course like we would like to have one atmosphere model for every star that we analyze, but this is just not feasible. But what we do is like we take this solar scaled stellar atmosphere models, and then on top we just do radiative transfer through that stellar atmosphere model. But then the actual lines that we measure, we just calculate the we just for the spectroscopic analysis, what we do is we just synthesize the actual lines that we observe, and then with like synthetic spectra, and then we just use the stellar atmosphere to just to do the radiative transfer throughout this atmosphere that is solar scale. So this is of course not the ideal situation, but we can, and this includes a bunch of systematics into the analysis, which are in the uncertainties of the abundances. But this is how we do this. We just scale the for the atmosphere models, we just scale from the solar abundance, if that makes sense.
No, my question was in the other way. Like, how long in evolutionary time does it take?
Okay.
Let's say, so you have a star, it formed, and then it produced the R elements in any way, and it has to be incorporated in another star. That is the star that you are missing. How long?
Okay, I answered a question that was like completely not your question at all. So sorry for that. So we can actually take, that depends on the stellar mass, I guess, but also depends on your metal mixing timescales assumption. We can actually have a sense of this from this work with this Reticulum II galaxy. So what we see from this Reticulum II galaxy is that the star formation of this galaxy is very, very short. The star formation duration is very, very short. However, we see that most of the stars in this galaxy, they are process enhanced. So what must have happened is that your metal mixing time scale must have been shorter than the duration of the star formation in this one galaxy specifically. So we see that for this one galaxy specifically, I'm not saying that this is valid for all galaxies. I'm not saying that this is valid for all dwarf galaxies, but for this galaxy specifically, we know that the time scale for the metal mixing has to be shorter than the duration of star formation. And this star formation duration is like very short. It's like less than 1 giga-year.
Yeah, but
So
in
this
that
is
case, you need to have like supernova to produce the R elements.
Yes, we don't know if it's core collapse supernova because we know that this R process in this galaxy, again, in this galaxy specifically, the R process event happened really fast. So we don't know if it's just core collapse supernova. We might be tempted to say that it's core collapse supernova just because the time scale is very short. But whenever you talk to the people that do neutron star merger modeling, they say that yes, you can actually have a fast merging neutron star. I don't know exactly how that happens. So, but this is the situation right now. From the abundances, we can actually tell because we just don't know the yields of these events. But what we can tell is that the time scale, not only for the actual R process event was really short, but also the metal mixing time scale was also very short for this galaxy. And I would be tempted to say that this was probably core collapse supernova, one of those magnetorotational supernova that I mentioned in the beginning. But if you talk to the neutron star merger people, the gravitational wave people, they say that you can have fast merging neutron stars that could do this. So I don't know, but this is the situation right now. Does that answer your question?
Yeah, yes, thank you very much.
More questions from the students? No? I have one that I took notes while you were presenting. When you have your explanation of the the cumulative star formation history versus age cartoon for fornax, toroidal versus sculpture. I just had it. The previous two slides, I think, that you just went through. Yes, that one. How can you reconcile fornax being like continuously always without the burst in the beginning if it has 6 globular clusters compared to sculpture that has none?
Okay, can you repeat that? I don't think I got the last part.
No, so fornax is a special galaxy, like it has 6 metal core globular clusters, right?
Yeah.
Sculpture has none. And supposedly these GCs were formed at the same time, sometime in the past. And to have formation of such objects, you need some burst.
Yeah, okay, very
So
high
how
star
does it
formation
work?
at early times.
Yeah, how does it work then, like fornax and sculpture to be so different in your cartoon?
Yeah, I think this is one thing that we are just not taking into account when you do this. I don't know. It's not what I did, but what these people did in this paper. They don't account for that. But this is one of the things that what I mentioned when I mentioned that we would like to have a single galaxy that we see this rising trend within the same galaxy is because of this. It's because by comparing two galaxies, you're just folding in a bunch of assumptions regarding your star formation history and also your chemical evolution overall, that it is just we just cannot make a lot of take a whole lot of conclusions from that because you're just folding in all of these assumptions. Having said that, I think the personalness of the star formation history in a given galaxy, like the intensity, the amount of the star formation rate at early times wouldn't affect specifically in this case. Because what happens is that what we are using in the vertical axis in this figure right here is the ratio between the R process element and the core collapse supernova element, which is magnesium. So what would happen is that if you have let's imagine I guess this I'm making more assumption now, but let's imagine that you have a very bursty star formation history in the beginning. So you have a lot of star formation happening very early on, which is like motivated for the amount of globular clusters that we have in Fornax. What you would have is that this ratio between these elements do not depend on the amount of stars that you are forming, because you're doing the ratio. You're doing the because so it unless you are having some weird things happening that for some reason you would change the ratio. Let's imagining that core collapse supernova, that those magnetorotational supernova, they do happen, and they are like in the midst of like all of the supernova that is happening early on. Unless for some reason there is a different ratio between these two kinds of supernova, that wouldn't change anything because specifically because we are doing the ratio between these elements. So what matters is only the ratio. So if let's say like if you form like 100 supernova, out of those only one is magnetorotation supernova, and now if you form 1,000 supernova, you would just scale that. Like first assumption is that you would just scale that, and you would have 10 magnetorotational supernova. So this is what would happen in this case. So specifically for looking at this ratio, and this is why we look at the ratio, we wouldn't have anything like changing because of that. Does that make sense?
Okay. More questions? I have one more, the last one.
Please go ahead.
Talk a little bit more about what photometric bands the MAGIC survey is going to use and why it's so special.
Okay, yeah, so this survey right here is just using a calcium HNK band on the dark energy camera, which is like Blanco at Cerro Tololo. So it's not very special, actually. There's a bunch of surveys that are already using this kind of narrow band filters. For instance, like in Brazil, we have like S+. It has an identical band to this one. You also have in the Northern Hemisphere, we have this survey that is called the Pristine Survey. They use CFHT Megacan with this same filter, but in the Northern Hemisphere. And we even have one of these filters in Hubble. So we can actually do this photometry with Hubble. The difference with MAGIC survey is that this filter is now on the dark energy camera. So you just have a humongous field of view for every pointing. So for us to have like a sense of this, you can just have the entirety of like Fornax or the entirety of Sculptor dwarf galaxies in a single pointing. So you can just have like there is actually one student that is working on doing like photometric metallicities for Sculptor specifically, and you just have 4,000 metallicities in the field of view, or 4,000 members of the galaxy. Not even all the stars in the field. You just have 4,000 metallicities for the galaxy in a single pointing. So this is why this is special. It's because it's going to be very, very efficient of finding the stars that we care about in these dwarf galaxies because of the humongous field of view of the dark energy camera. And then because you just already have a bunch of photometry from like dark energy survey or DCAN overall, covering a bunch of the southern hemisphere, what you can do is just combine that metallicity sensitive photometry, the narrow band photometry, with other broadband photometry for you just derive metallicities, because what you need is just some sense of the color of your star. And if we imagine for a dwarf galaxy, you just know the distance. So if you just know the distance, then you know the evolutionary stage of your star, because you just know what brightness they should have. So then you just have like a surface gravity for your star from the distance of your dwarf galaxy. And then you just fold in the metallicity sensitive photometry for you to get a metallicity. So this is the difference because it's in dark energy camera. And I guess it's also the difference that it's in the southern hemisphere. So you get the Magellanic clouds because of that. So this is very useful as well.
I think Marina has a question. Do you want to open your microphone?
Okay, I can open the microphone. Hi, Guilherme. Thank you very much for the very nice talk. I have a question. Since it depends on the mass of the star, so I think that these abundances, the abundances ratios probably depend on the IMF, right? Do you take this into account?
We do not. Yes, you're absolutely right. So this is one thing that is classically known to depend on the like especially the alpha elements are going to be like really dependent on the IMF.
Mm-hmm.
But we just assume that's universal IMF. So you're right. If you're changing IMF from galaxy to galaxy, this is going to be introduce a lot more complication. Having said that, alpha elements are just the thing is that what I have decided is that alpha elements are very difficult to measure. Because
Okay.
alpha element, this magnesium, the lines are very strong, but the lines are always saturated. So because of just systematic uncertainties alone, the difference that you would have from one IMF to another, it is going to be just folded in with the uncertainties of your, they are just going to be within the uncertainties of specifically your magnesium abundances, or your alpha element abundances, just because alpha element abundances just have a lot of uncertainties anyway, because if you're taking care of your uncertainties correctly, because you just have a bunch of systematics already. So I don't think the conclusions the qualitative conclusions would change from everything that I just showed right here.
Okay.
However, the details would indeed be dependent on the IMF, just like you
Okay.
said.
Okay. Okay.
Does
Thank
that
you.
make sense?
Yes. Yes.
Okay.
Okay, more questions? I have one that I'll send through email later on. So let's thank Guilherme again for the very nice talk. And, good luck with your finalization of the thesis. Very nice work.
Thank you. And tchau para todo mundo aí.
E a gente tem café agora.